Okay, so we are on number 10 on the practice problem set. It says a 95 degrees Celsius cup of coffee is set down on a counter where the room temperature is constant at 20 degrees Celsius. As the coffee cools, the following temperature data is collected. We're going to predict the temperature of the coffee 14 minutes after the cup was set down on the counter, and then find out how long it takes to get to 40 degrees Celsius. But first we're going to need the model. So since this is cooling, this is a Newton's law of cooling problem. And remember that the PTD relationship for Newton's law of cooling is object minus room. That's supposed to be a minus sign there, and that didn't do a very good job. Object minus room. And the room is 20 degrees Celsius. So this is going to be our T of T function. So we're going to ultimately, after we get, actually let me erase this for the moment. After we get do our regression on this data set, then to get the T of T function, we'll have to remember to add the room temperature back in to get the object temperature. So we need to go to the calculator and enter this data. I actually did that already. So I've got my data entered in the calculator. And now for column L3, because I need to do the regression on the temperature difference, so for column L3 I'm going to do column L2 minus 20 degrees. Okay, so that's my PTD data. And now to do the regression, we will do exponential regression on L1 and L3. Remember that we have to change that to L3 because of this PTD stuff. So there's our regression function. This is the PTD function. That's what we just found. And now what I ultimately want is T of T, the object temperature at time t. And so to get that, I'm actually going to go, basically I go to this relationship and I say, well, the object temperature must be equal to the PTD plus the room. So we need to go to our PTD function, which is saved here, and add the room temperature. So the way I like to do that is to insert the room temperature, which is 20 degrees, in the beginning, and then add that to my function. And so now I actually have the true object temperature function. So if you want to know how long or the temperature after 14 minutes, we can just do vars y vars function y1 of 14. And we get 65 degrees, or 66 degrees, I guess. Rounding to the nearest degree. And to find how long it will take for the coffee to get to 40 degrees, that will be a calc intersect question. So I need to have 40 degrees here as my y2. Let's go to the table. This happens between 37 and 42 minutes. I will set an increment of 5. So actually this window would be okay, but we can just, let's do 50. And then do zoom fit. And then we should see our intersection over here somewhere. Okay, so we just got it there. And the time is 37.87 minutes. Okay. So 65.93 degrees for part A, 37.87 for part B. Okay, let's look at number 11. Solve the linear system 4x minus 3y plus z equals 3, so on and so forth. All right, So what I notice about this right off the bat is I have 3 variables. So I'm going to need to arrange my system appropriately. Arrange my windows too. So the first one is actually fine. I can leave it as is. The second one we do need to do a little work to. So that's going to be 6x plus 0y, because there's no 0, but we need to represent it anyway, equals 4. And the third one is 2x plus 3y minus 2z equals 11. So it's important that we rearrange the system to be consistent throughout. And the standard thing to do is to put the variables in this order. Also, that should say it's a y. I know it looks like an x, but that's 4x minus 3y plus z. And that now our coefficient matrix will be 4, minus 3, 1, 6, 0, 4, 2, 3, minus 2. And then this is x, y, z equals 3, 4, 11. And so now we're just going to enter all these coefficients. This will be matrix A, this will be matrix B, and then I'm going to, after I've entered them, I'll find the inverse of this matrix and multiply it by this matrix. And that'll be the solution to our system. Okay, I'm going to do some of this off camera. Alright, so I just entered the A matrix. Before I leave the screen, I want to point out a couple of things. Make sure when you're, first of all, make sure that you put the right dimension in. This is a 3 by 3 matrix, so you've got to make sure that you tell the calculator that. Also, when you're entering your values, some of these values are negatives. So just make sure that you put a negative, you use the negative sign and not the minus sign. If you use the minus sign, it won't be happy. So you've got to use the negative sign. So, okay. And now let's enter matrix B. This is going to be a 3 by 1. And its values are 3, 4, 11. Okay. Now I just need to call the matrices back up, invert A, and multiply it by B. And there we go, 2, 1, negative 2. So this is that's a Z right there. Okay. And that's number 11. How about number 12? A quantity increases by 1.2% each week. What is its weekly continuous growth rate? So let's clearly identify what we have and what we're trying to do here. This is the weekly growth rate. And I'll go ahead, I'll say weekly standard growth rate is 1.2%, or in decimal form, that's 0.012. Okay, so in other words, this is R. And what I want is RC. So I'm trying to convert this R to RC. Now, I don't have to, this is not a time unit change because this is weekly and this is weekly, so we don't have to change the time unit. We just need to go from R to RC. So let's go look at our equation list to check in what equations we have for that. And look right here, the last one is the one that we want. It's giving you RC in terms of R. So really what we just need to do is get the factor, and that means we need to add 1 to our growth rate and then take the natural log of that factor. So RC is ln of 1 plus R, which in this case that's going to be ln of 1 plus 0.012. Sorry about my bad handwriting. So we need to take the natural log of all of that. So that will be ln of 1 plus 0.012. And let's multiply that by 100 to get it in percent form. And there you go. There is our continuous weekly growth rate. 4 decimal places, that would be 1.1929. 1.1929. Very good. All right, number 13. A material decays continuously at a rate of 0.872%. All right, so we have a continuous decay. Now, that means that our growth rate, our continuous growth rate, RC, is negative 0.00872. So be careful about that, because everything's going to be kind of phrased in terms of this continuous growth rate, but since it is actually decaying, I've got to change the sign of this. That would be a very common mistake to make, is to forget to change that sign, in addition to turning it into a decimal form, non-percent form. All right, so with that in mind, if I want to find the half-life of this, I'm going to need, basically I need the model. And since I don't have an initial value, let's assume that our initial value is 1. And then this is, since it's continuous, we're going to be using the continuous growth or decay model. So this is e raised to the negative 0.00872t. That's my function. Okay. To find the half-life, I just want to know how long it takes this to get to 1/2, because my initial amount was 1. And so we want to know how long it takes to get to 1/2, which will be a calc intersect question. So that's 1 times e to the negative 0.00872x, and then y2 is 1/2, 0.5. My table, actually this isn't bad. I happen to be set on increments of 5, so this will get me there pretty quickly. You see it happens between 77 and 82, but if you are starting off from 0, you've got to be careful to check your table and see what your window should be. So I'm gonna put this at 100, and then do zoom fit. So there's our intersection, and this represents our doubling time. So we'll do calc intersect. And that's 79.49. So that's years. 79.49 years. Let's find the annual decay rate, part B. So the annual decay rate this is the standard yearly decay rate, right? So what we're going to start with is the factor, which is e to the negative 0.00872. This is the yearly factor. Yearly factor. And remember that r equals e to the rc minus 1. So if we say e to the negative 0.00872, no variable, and then subtract 1 from all of that, we will get r, which is the growth rate, right? So we want the decay rate, but that'll get us the growth rate, and then we'll just need to change the sign of that value. I think I'm going to have to finish this problem in the next video, so I'm going to pause here.